Lab 3, Black Hole. The purpose of this lab is to observe the motion of a star around a black hole and then to find the mass of the black hole using glow script to see the forces acting on the star's orbit. By observing the motion of the star around the black hole, we can assume that the only force acting on it is the gravitational force of the black hole, and with this information we can solve for the mass with the gravitational force formula, keeping in mind that the net force equals the force of net parallel plus the force of net perpendicular. For glow script, I started out this lab by plugging in my email into the seed. I added the gravitational constant, which is 6.7 times 10 to the negative 11, and the mass of the star, which is 2 times 10 to the 30 kilograms, and set the time equal to 1 day, which is 86,400 seconds. Then in the calculation loop, I set the momentum vectors to be equal to the star's mass times the velocity, and then changed delta p and delta v to match the two previous sections of coding, and the equation would be final minus initial to show the change in velocity and the change in momentum. To calculate the net force equation, I manipulated the force equation, force equals ma, to force equals the change in momentum over the change in time, and then calculated the net force parallel equation. To find the perpendicular net force, I took the net forces and subtracted it from the parallel net force, and then created arrows to represent the vectors, which you can see in the video on the next slide. And to calculate the mass of the black hole, I manipulated the gravitational force equation to be equal to the mass of the black hole, and to calculate the mass average, I used Google Sheets to do so, which will be seen in the next few slides. Here's my glow script video, and as you can see, the net force is the orange arrow, the net parallel force is the pink arrow, and the net perpendicular force is the blue arrow. And the yellow ball is the star, and the black ball is the black hole, and the green circle the star's orbiting is the motion that the star is going around with the gravitational force of the black hole. The average mass of the black hole was 9.87 e 33 kilograms. The net parallel was 1.757 e 29 newtons, and the net parallel was 4.21 e 28 newtons, and the net perpendicular was 1.49 e 29 newtons. And all of these averages were calculated in Google Sheets, which you can see on the next slide. Here is my Google Sheets that I created to find the averages of all the information to sum up for each of the times intervals. So what does this mean? The net force and its parallel net force and the perpendicular net force are all equal to the change in momentum and the parallel and perpendicular changes in momentum as well. And this is because when the net force equation is derived from force equals ma, you get that force equals delta p over delta t, which would be equivalent to the parallel and perpendicular net forces, as well as the momentum components that equal the net force components, which you can see on the slide above, are all the equations I listed. What if? If the black hole was exchanged to a different black hole and the motion of the star remained unchanged, that means that the force of the black hole and the mass would stay the same because the star is still moving as it was before. You would not be able to tell the difference between the two black holes. If the mass of the black hole changes, there would be a change in the momentum, which would change the force, which means there would have to be a new acceleration to adapt for the changes in mass, which can be seen in the two equations above as well, because the force of gravity equals ma, which also equals gravitational constant times mass of the star times mass of the black hole over position squared. Thank you so much.